Greetings, this is Mr. Garwood with our continuing video series on Calculus 2nd edition by Briggs, Cochran, and Gillette. In our previous videos, we have been setting up the idea of a derivative as the slope of a tangent line at a point. And this video is going to focus on the traditional definition of the derivative. We focused on the difference quotient with the change in y over the change in x, and this is going to work very, very similarly, but the idea is instead of defining another point that we're moving, we're going to talk about a distance from the point that we are interested in. So I have set up, once again, we're using f of x equals x squared, and I've got a tangent line sketch. I missed the point a little bit, I apologize, just pretend with me. And what we're going to do is, before we called this c and we had another x that we were bringing in much closer, what we're going to do now is we're going to define a distance from x. So what I'm going to do is I'm going to find another point, and I'm going to call that x plus h, which means that h equals delta x. H is the distance from the original point that our second point is. And just like before, I'm able to sketch a secant line between the 2 points of interest. And we can also talk about, so this point is now f of x plus h. And the question here is how can I set up a limit definition so that, just as before we said, we're still looking at as this point gets closest to this point, now we're looking at really what happens is h gets close to 0. And that's what I want you to see is as this distance gets really small, and by small I mean it gets very close to 0, can we set up a limit that describes how this relationship is going on. So in our last video, I set up the idea that dy dx is the derivative. It is the slope of the tangent line. And we define that as the limit as h goes to 0. Now before we did the limit as x goes to c, but here what I'm focusing on is this distance of my second point from the original point. How far away is it? And I'm saying the limit as that goes to 0 is, well, this y value, f of x plus h minus f of x, all over x plus h minus x. Now this is not how you're going to see it in your textbook. Traditionally what the writers do is they say, hey look, I've got a positive x here and I'm subtracting an x, so these two cancel, which means I can rewrite this as the limit as h goes to 0 of x plus h minus f of x over h. And this dy dx equals this is the definition of the derivative. In a classical sense, this is what the definition of the derivative is. So, for our purposes here, we're going to do exactly the same thing we did before. I'm going to plug in these values and evaluate them within the function. So I've got the limit as h goes to 0 of x plus h quantity squared minus x squared, and that's all over h. And then what I'm going to do is I'm going to do a little bit of algebra here. I need to expand x plus h squared. This is one of those, the perfect square thing, so I can say that that's x squared plus 2xh plus h squared minus x squared all over h. Now, if the bottom were not 0, I could just evaluate this by plugging it in, but here I've got 0, and that causes us problems. Now, what I also want to note is, hey look, just like we did above, I've got an x squared here, I've got a minus x squared here, those two cancel, which means I am left with the limit as h goes to 0 of 2xh plus h squared all over h. And hey look, there's an h in both terms in the numerator now, so that's the limit as h goes to 0 of h times 2x plus h all over h. And if we're minding our work here, we notice, hey look, I've got an h top and bottom. I'm not evaluating at h is 0, I'm looking at what it's doing around it, which means this whole thing so I run out of paper, comes over here and it's dy dx equals the limit as h goes to 0 of 2x plus h. Now, this is a polynomial, and our rules of polynomials say that, hey, look, all I've got to do is plug in here, and so I'm going to say that h is 0. Well, that's just 2 times x plus 0, which is just 2x. Now, if we go back to our findings in the previous video, we said the slope of the tangent line at any point was take the x-coordinate of that point and double it. Well, this is doing exactly the same thing. These two definitions of the derivative, though we work them out slightly different, result in the same value. On the parabola, if I pick any point, the slope of the tangent line at that point is twice the value of the x-coordinate. And what I really want to emphasize is that all we are doing when we're evaluating derivatives is we're looking at, for this function, at a particular value, what is the slope of the tangent line. And as we move forward, we are going to talk about the derivative as a function of the original function, but for our purposes now, if you give me a value of a function through these definitions, I will be able to derive the fact that at any particular value, the slope of that tangent line is there. I hope that you have found this video useful, and I wish you luck in the coming semester.